Hello, my name is Mateusz Buczkowski and today I will tell you about the Monte Carlo Simulation. But don't worry, it's not about the gambling, it's about very interesting mathematical approach. The Monte Carlo Simulation is a mathematical modeling method. It's used for computing complicated problems which are very difficult or sometimes impossible to solve traditional way. It has been developed by a Polish mathematician Stanisław Ulam, who has been working for United States government in 1940s during the development of the nuclear weapon program. In my professional life, I'm working for the construction and real estate industry, and I would like to show you how these methods can be implemented for cost estimating. In this video, I will not focus on the Monte Carlo simulation theory itself, because it will be long enough without this anyway. However, if you're interested, I can recommend you, of course, Wikipedia and YouTube course Introduction to Computational Thinking and Data Science, prepared by MIT OpenCourseWare. If you're interested, please find the links below. In order to implement this idea in reality, I have prepared an Python application which computes everything together and prepares the final result. I will show you at the end of this video. It is a non-commercial project. I did it for fun. So if you're interested, if you would like to see the code or if you would like to play with the app, please let me know. I will send you the file. Okay, so let's start the cost estimating statistical way. Let's imagine the client who comes to you and asks about the cost of building a new property, and he wants to establish a budget. The final product is the cost estimate, which has been prepared as an average of the collected data. And usually there's no matter if the client comes with just a concept folder or some very limited amount of data. Some other clients come with much more detailed documentation. However, usually what they get is a very similar product for everybody. For the concept and for the very initial stages, usually a higher contingency is being added. But why the contingency is set on 20 or 10%, and where did these numbers came from? It is something that the client is prepared for and everybody accepts because it's always been like this. But let's consider a different approach. If I asked you how much is the concrete in Warsaw per cubic meter, what would be the most natural answer? Is it one very specific number, or maybe it's some kind of range that everybody knows that it's between of this and that? Dependingly, of course, on the conditions, on the amount you can or you want to order, the delivery distance, and so on and so on. I would bet that much more natural and much more true actually is to say that the concrete in Warsaw today is between 200 and 250 than just giving an average of 225. So what we usually do is we take all the historical data we have and we compare it to the data we obtained from the client. However, instead of putting our effort into compressing and averaging everything, maybe let's consider a different way. From all the data we have available, let's take minimal and maximal values. And this may not refer only to the unit prices, this may be the quantities or currency risk, interest rates, everything that combines into the final forecasted budget to the client. If we had to guess at this point, we know that both of those cost estimates, optimistic and pessimistic, they are not something that we will end up with. The final outcome will be something in between though. So how much our client will pay at the end? Let's jump in the future for a while. Let's imagine that instead of the conceptual design or some kind of assumptions for the property we want to build, let's assume that we are 1 year in future and we have a complete design prepared for the investment. What we are going to do, we will go to the market and we ask the contractors for the price for each scope. Assuming that we know the market and the conditions, all the offers from all the contractors for all the scopes should be within our min and maximum values for each position. And of course we don't know at the moment which scope will be closer to the maximum and which scope will be a little bit lower, but everything together is like on our example will be somewhere in between 12 and 32. Let's see our example cost estimate. What we would normally have done would be taking averages for quantities and unit prices in each position and multiplying them together, which would result with the average of 22. After adding a proper contingency, this would result about 26. But let's do something different. Let's pick the random value for each pair of the values and put it together like it was combined offers from the several subcontractors. What we have then is a random cost estimate, which of course doesn't have a real background, and it's not very useful for us by itself, as it's one of thousands or millions possible combinations. But what happens if we prepare thousands of this kind of cost estimates, each time taking a random numbers for each position? And this is the moment when we can say that the magic happens, because not every total sum has the same probability of occurrence. Please have a look. This is the histogram exported from my application, which shows how it looks for 1000 iterations of our cost estimate. And as you can see, the values below 80, 70 are much less probable than the value in the middle of the scope, and values higher than 26 are also not the same probable as, for instance, 22. If we compare it to the traditional method, we can see that we still can give an average to the client that 50% of our population is less than 20.97. It's a left half of our histogram, but this time we can say something more to the client, because 21 is, let's say, expected value for this cost estimate. However, probability of keeping the budget at this level is 50%, which is usually not very interesting for the client. And if I was the client, I would like to be at least 80 or 90% sure. And as you can see, we can give these values to the client as well. In the table below, we have a position called error. Not going too much into statistical details, it can be proved that repeating and repeating our simulation one time after another, our results will not be different more than 1% from what we have here. And this is the example for the real cost estimate for the building which have been tendered here in Warsaw some time ago. As you can see, the average value for this is 180 million zlotys, and 90% of the population of the cost estimates is below 190 million, which for me would be a safe value for establishing a budget. One of the real advantages of this method is that it really helps to evaluate the quality of the data we are putting into. Let's see on this slide. Just on purpose, I have reduced the quality of the data in the chart below. So this is the same cost estimate, the same 54 positions breakdown. However, I have widened some values in a couple of important positions, which theoretically might be due to imprecisement or lack of confidence for those positions. So as you can see, the Gauss curve became a little bit more flat and a little bit wider, It means that in order to chase our 90% confidence level we want to achieve, we have to go a little bit more right. It means that we need to put additional money into the budget to cover the risk of landing in this area. So, as I mentioned before, the Monte Carlo simulation has been developed in 1940s. Since that time, it has been implemented in many professional and business fields like finance, project management, energy, manufacturing. For instance, we may use it for forecasting of the weather and assuming humidity, temperature, air pressure, and so on. Regarding some pros of this method, as I mentioned before, it's not only predicting the result we are expecting, but also it allows us to assess the quality of data we have. After we have the first impression of the quality of our data and the first outcome of our model, we can search for the weakest points in it. This is called the sensitivity analysis, and it allows us to find the scopes or the areas where the data is the less precise. So maybe instead of telling to the client that you can be only 60 or 70% sure, because getting to 90% would require doubling the budget, we may say that it's better to improve some areas of our data. For instance, we do our homework and we go to the land surveyor, do some measurements, or we prepare some foundation design, some ground survey, something which allows us to be much more precise in that fields. So after another iteration of our model, the values will be much closer one another. Of course, this model has also some cons. We have to really think about how we are preparing the model, because if it's not reflecting the reality, the results will also be not true. The assumptions we make have to be fair and correspond with reality. And of course, in these kind of models, usually we don't assume extreme events, so the model doesn't take into consideration some really extraordinary events like financial crisis, bankruptcy of one of the companies, and so on and so on. Okay, so now it's time for our application. I will shortly show you how it works. Here you have the code. As I mentioned before, if you're interested, I can distribute it. Please let me know. Probably some professional Python programmer would write it in less than 600 lines, but let's leave it. We have just loaded typical table, the same that we had in our presentation. We can see it here. So we have 4 tasks with very simple numbers. Then we make an analysis of the data. So by default it prepares 1000 cost estimates, which usually is enough. We can see the histogram. We can also check the cumulative chart as well. The application displays some basic parameters of the population. So we have the number of iterations. As you saw before on the presentation, we have the mean, standard deviation, and so on and so on. And the final feature is the sensitivity analysis. I will show you how it looks like. The data is very raw, as you can see. However, it's for me, so I know how to use it. Here we have all the tasks, and here you can see how this task influence the complete cost estimate. Because they are the same, the result is the same as well. But let's do something different. So here we have this model of the real cost estimate. And this is like histogram looks. Okay, so that's all for today. I hope you found this material interesting. If you have any ideas, please leave me the comment below or just send me an email. Take care, bye.